Hello everyone. Today we're going to learn part 2 of operational amplifiers. Here are the module objectives. First, we're going to learn semi-ideal op-amp model. We're going to look at the problem-solving procedures by using ideal op-amp model. And we're also going to look at some applications as well as the design examples. Let's first look at a semi-ideal op-amp model. A semi-ideal op-amp model is an intermediate model which is more accurate than the ideal op-amp model, but less than the linear model. In semi-ideal op-amp model, it assumes Ri that is equal to infinity, Ro that is equal to 0, and A that is equal to A naught. Here is the circuit representation. If we model a circuit on the left, by using the semi-ideal model will be shown on the right, where we can remove this op-amp device, which will open the two terminals. The voltage difference between the two terminals is called a Vin. And on the output side, it is modeled as a voltage-dependent voltage source, and the amplification gain is AO. By giving these assumptions, and the conclusions are also different. Since Ri that is equal to infinity, which implies the current goes into the op-amp device that is almost 0. So we have I plus that is equal to I minus that is equal to 0. Since the amplification gain is a limited number, V plus and V minus, they are no longer the same. So this part will be represented by another equation, which is VO is equal to AO times Vin. Vin that is equal to V plus minus V minus. So in ideal op-amp model, we have the assumptions of Ri that is equal to infinity, Io is equal to 0, and A that is equal to infinity. By giving that, we have the conclusion of I plus that is equal to I minus is equal to 0, and V plus is equal to V minus. In semi-ideal model, the difference is that A that is no longer infinity, A is a limited number of AO now. So the conclusion that we have is I plus is equal to I minus is equal to 0, and VO that is equal to AO times V plus minus V minus. The problem-solving procedure using ideal op-amp model. Since it is much easier to employ the ideal op-amp model rather than the nonlinear models, unless otherwise stated, we will use the ideal op-amp model assumptions to analyze the circuits that contain operational amplifiers. The problem-solving strategy. The first step is to state we're going to use the ideal op-amp model for analysis, where we have the assumption of AO that is equal to infinity, Ri that is equal to infinity, and Ro that is equal to 0, which implies that I plus that is equal to I minus that is equal to 0, and V plus is equal to V minus. The second step is to apply the nodal analysis to the resulting circuit, or you can write a KCL equations at different nodes. Step 3 is to solve the nodal equations to find out the relationship between the output and input signals. And step 4 is to draw a conclusion. Let's look at one application, comparators. Here is an ideal comparator and it's a transfer curve on the right. In a comparator application, one signal is connected to V plus node and the other signal is to V minus node. We know that if V plus is higher than V minus, we know the output will be VCC, which is also shown in this transfer curve. So V plus minus V minus is greater than 0, the output will be VCC. Otherwise, if V plus that is less than V minus, we will have the output of VEE. On the transfer curve is this section. A special case of a comparator is called a zero crossing detector, where one signal Vs is compared to the other signal connected to the ground. We can also find its transfer curve in the right figure. If we have a sinusoidal input, which is indicated by this yellow line over here, as long as Vs is greater than 0, and we'll have the output, which is equal to VCC, in this case that is 5 volts. As is less than 0, we will receive the output of a negative 5 volts, which is indicated in this section. And putting all this together, by providing the sinusoidal input, the output becomes a square wave. The only difference that we didn't see from this zero crossing detector is this pull-up resistor. Whether we will need this pull-up resistor depends on the manufacturer or the chips that we're going to use. And in this table, I provided two products, which is the LM339 and the other one is the MAX 919. And on the description, we can see that for LM339, it requires a typical pull-up resistor, which is 3K ohm, while for the other op-amp, MAX 919, it doesn't need a pull-up resistor. Let's look at one design example, a line meter. We're going to select a value of R that will produce an output voltage of 1 volt for each 10 microamp of a sensor current. Assume that the sensor has zero resistance. The first step is to come up with a possible solution. Over here, we have a light sensor. If the light sensor receives light, it will produce a current. And this current is very tiny at the microamp level. Here we set it up as a typical amplification application, where we have a feedback resistor connected from the output to the inverting terminal. So this is called a. So the second step is to come with the design equations. We're going to use the ideal op-amp model for analysis. It implies that V plus is equal to V minus, and I minus is equal to I plus that is equal to 0. Then we can apply KCL at this inverting terminal. If we count the current that goes into the node V minus, that is equal to the current leaving the node, we have the equation of a VO minus V minus divided by R minus the current leaving the node I, that is equal to the current leaving the node I minus. Step 3, we can solve the equation. So on the right hand side, I minus that equal to 0, V minus equal to 0. So we can find that VO over I that is equal to R. This is how we can find R that is equal to 100 kilo ohm. So step 4, we just need to draw the conclusion, say R that is equal to 100 kilo ohm. This design example is a voltage step-down circuit. Over here, we're going to reduce a very large input voltage range between plus minus 680 volts to a small output voltage in the range of minus plus 5 volts, use only 2 resistors. The first step is to come with a possible design. Since we must reduce a positive 680 volts to negative 5 volts, we can consider using our inverting amplifier. So this picture gives a typical setup. The second step to come with the design equations, the same, we're going to use the ideal op-amp model. It implies that V plus is equal to V minus and I plus is equal to I minus that is equal to 0. We can apply KCL at the inverting terminal, which gives us VO minus V minus divided by R2 plus V in minus V minus divided by R1 that is equal to the current leaving this node, which is I minus. By combining the equations, we can solve them. Since in this equation, we can see that I minus is equal to 0, V minus is equal to V plus, and V plus is connected to the ground. V plus is also equal to 0. We know that V minus is equal to 0. This is 0. So we can find a relationship between VO and V in that is equal to negative R2 over R1, which is equal to negative 1 over 136. So step 4 is to draw a conclusion. So we can choose from the standard resistors by selecting R1 that is equal to 27 kilo ohm and R2 that is equal to 200 ohm. This design example is to design a desired amplifier. The design specification requires VO over V in that is equal to 10, or we can say amplification gain that is equal to 10. And the input is within a range of negative 2 to 2 volts. There is additional requirement of a power loss in the resistors should not exceed 100 milliwatts. The first step is to come with a possible solution. Since this is a non-inverting amplification, we'll set it up as a non-inverting amplification application. So the input signal is connected to the non-inverting terminal, and there is a resistor network connected between the inverting terminal and the output. The second step is to come with the design equations. The way to come with the design equations is the same as what we did for the previous two examples. We will use ideal op-amp model, implies the voltage at the inverting terminal and non-inverting terminal, they're the same, and the current goes into the two terminals are 0. And we can write a KCL equations at this inverting terminal, which give us VO minus V minus divided by R2 plus 0 minus V minus divided by R1, that is equal to the current I minus. By simplifying that, we get the conclusion VO over Vin, that is equal to 1 plus R2 over R1. From the design specification, we know that this amplification gain needs to be equal to 10, so we can find the relationship between R2 and R1. The second requirement is a power loss, happening at the resistors connected to the output terminal over here. Since I minus is equal to 0, so the current in this branch is equal to 0, the power loss becomes VO squared over R1 and R2. So this is the same way how we calculate power consumption by resistors. From that, we can find another requirement, R1 plus R2 that should be greater or equal to 4 kilo ohm. Step 3 to solve the equations, R2 that is equal to 9 R1 and R1 that is greater than 400 ohm. And step 4 is to select the resistors according to these two requirements. The next design example is to come up with an operation circuit. The output that is equal to a linear combination of two input, and both of them have a negative sign in front of them. So it implies that both of the two signals, V1 and V2, that are connected to the inverting terminal. The first step is to come with a possible solution. We have V1 and V2 connected to the inverting terminal through two resistors, R1 and R2. At the same time, we have another resistor connected from the output to inverting terminal. The second step is to come up with design equations. And since the non-inverting terminal here is connected to the ground, we know that V plus is equal to 0. And at this inverting terminal, we can apply KCL, which give us VO minus V minus divided by R plus V1 divided by R1 plus V2 divided by R2, that is equal to the current leaving the node, which is I minus, which is the same as the equation that we have here. The step 3 is to solve the equations. By solving the above equations, we find a relationship R that is equal to 0.9 R1 and is equal to 0.1 R2. There are additional requirements for this problem, so we need to minimize the power dissipated. So the power dissipated in the circuit are in three parts: the two resistors from the two input signals and one resistor from the output side. So the power consumption that is equal to VO squared divided by R plus V1 squared divided by R1 plus V2 squared divided by R2. We know that to minimize the power dissipation, we need to increase the resistance. And there is an additional requirement to say the resistors no larger than 10K. So from here, we know that R2, that is the largest resistor, because all the others are smaller than this. So we're going to select R2 to be 10K, so that we can find a R, which is 0.1 of R2, which is become 1K, and R1 that is 1.1K. So let's summarize all the applications we have learned so far. The first one is a unit buffer, or we can also call it a voltage follower. We have one wire connected from the output directly to the inverting terminal. We can have VO that is equal to VS. The second application is a non-inverting amplifier. In this application, the input signal will be connected to the non-inverting terminal, and the resistor network will be connected on the inverting terminal. The third application is an inverting amplifier, where the signal will connected to the negative terminal or the inverting terminal. So does the network. If that's a setup, VO over Vin that is equal to negative R2 over R1. The third application is a comparator. where the output VO will be either VCC or VEE, depends on which signal that is larger. The next application is a summation application, where we have two signals connected to the same terminal. And if they have a negative sign, we can connect both of two signals to the inverting terminal. If we have plus sign, the signals will be connected to the non-inverting terminal. The next is a subtraction application, where we have two signals connected to different terminals of this operation amplifier, and the output and the input relationship is given in the formula. That's all for today's lecture.